Picture a delivery driver with 20 stops. How do you find the single shortest route that visits every stop once and returns home? This is the Traveling Salesman Problem, and today we'll crack it with the Held-Karp Algorithm. Let's define it precisely. You're given a set of cities and the distance between every pair. Your goal is the shortest possible tour that visits each city exactly once and returns to where you started. In graph theory, this is a minimum cost Hamiltonian cycle on a complete weighted graph. We store those distances in an adjacency matrix, and if two cities aren't connected, we set that weight to infinity. So why not just try everything? The brute force approach lists every possible ordering of cities. For n cities, that's n factorial routes. This is fine for a handful of stops, but m factorial explodes. At just 15 cities, you're already past a trillion permutations, far too many to check one by one. Dynamic programming changes the game. Instead of n factorial, Held-Karp runs in order n squared times 2 to the n. That's still exponential, but far tamer, pushing the practical limit up to around 20 cities on an ordinary computer. The key idea? Solve the shortest subpaths once, store them, and reuse them to build longer paths, so we never compute the same partial tour twice. To reuse work, we need a state. A state captures two things: the exact set of cities we've already visited, and the last city we're standing in. Why the last city? Because to extend the tour, we must know where we currently are. With n possible last cities and 2 to the n possible visited sets, our memo table has size n by 2 to the n. How do we store a set of visited cities cheaply? With a bitmask. We pack the whole set into a single integer. If city I has been visited, bit I is 1. If not, it stays 0. Visited cities 0 and 1, that's binary 1, 1, which is 3. Cities 0 and 3, binary 1, 0, 0, 1, which is 9. Now, bitwise operations let us update and test the set almost instantly. Now the algorithm, step by step. First, initialization. Pick a fixed star city, usually city 0. Fill the whole DP table with infinity. Then set the base cases. For every other city I, record the direct distance from the start to I. In the state whose visited set is just the start and I ending at I. Next, the heart of the algorithm. Expansion. We grow paths by length. For each subset of cities of a given size that includes the start, we look at every possible last city in that subset. To reach it cheaply, we drop that city from the set, take the best cost of the smaller subset ending somewhere else, and add the edge into our target. We try every predecessor and keep the minimum. When the loops finish, we hold the best cost for every full path. The bitmask, that's all once. But a tour has to come home. So we take each possible final city, add the edge back to the start, and keep the smallest total. That value is the minimum cost of the whole tour. The cost alone isn't the route, so we reconstruct it backward. Starting from the full set, we ask which previous city produced the optimal cost we stored. We record it, clear its bit to step back in time, and repeat until we return to the start. Link the end back home, and the optimal tour is revealed. And that's Held-Karp. By encoding tours as states and moving through them with fast bitwise operations, we skip mountains of redundant work. The factorial explosion becomes a manageable, exponential, and problems that were hopeless by brute force fall within reach. You now have everything you need to implement it yourself.